Hey guys, this cycle is all about taking what we were working on as far as function notation and adapting that to deal with equations. So we're going to have some actual equations for our mother functions, not just dealing with f of x and g of x, and have to get used to dealing with that type of thing as well. First off, we're going to take a look at some different functions that we might use, and I'm going to start off with the equation y equals x squared. I'm going to choose some decent values for x, and by that I'm going to choose points that will give me values I can hit on here. I know I can definitely get 0, because 0 squared is 0, that shows up. And let's go 1 point on either side, -1, +1, that'll be 1 and 1 respectively. So that gives me those. And then I know I can go 1 point on either side of that. -2 and +2, which is not going to give me 2, it'll give me 4 on both sides. And that'll be like that. If I try to go up to 3, that would be 9, which is now off my paper somewhere up here. So I've got something that looks like this. And from Algebra 1, you remember these are called parabolas. This is a quadratic function. It's quadratic. It comes from the Latin for a word meaning to square something. And in terms of cycle 8, if you look at your graphs, you can see this matches up with f of x. For our next one, we've got square root of x, and let's try the same point. So if I try -2, square root of -2, oh man, that doesn't actually work. It gives me what we call an imaginary number. And if you try that in a calculator, it's going to give you an error. And in terms of stuff that we have so far, we don't have enough math yet to really understand what's going on there. So, I don't know, I think the first number I can plug in is 0. And square root of 0 is going to be 0. Okay, right on. Nice. And then I plug in 1. Square root of 1 is 1. We're good. If I plug in 2, square root of 2, it's 1.414. I don't really like that. So I'm going to try to limit this to numbers that give me nice clean square roots. So the next perfect square I have is 4. That'll give me 2. And the next perfect square I have is 9. And that'll give me 3, which is somewhere like there. And the next perfect square I have is 16, which would be 4, but that'd be way off our graph, so we're not going to worry about that. And when I connect these dots, and hopefully you do a better job than I did, I'll make my point bigger so it hits. We have a graph that looks something like this. In cycle 8, I believe we call this graph g of x, and it's a square root function. So I paired these two together, f of x and g of x. And the reason that I did is going to be kind of based on what we were talking about at the end of our last cycle. So if I look at the table we had a minute ago, which was -2, 4, -1, 1, 0, 0, and then we got 1, 1, and 2, 4. I'd like you to notice that these points end up having a lot to do with what's going on in our... Oh, wait a minute, those are backwards. So these points of x's and y's are switched. And the thing we talked about in the last cycle is that these are inverses. I'd also like you to notice that there's a connection between x squared and the square root of x. That if we square something, it's kind of the opposite. In fact, literally is the opposite of taking the square root of something. Next up, we've got x cubed. I think we're going to be pretty good on this one to just use our standard -2, -1, 0, 1, 2. And then we got -8, -1, 0, 1, 8. So that gives me something like that. We've got 1, 1, 2, 8, -1, -1, and -2, -8. Nice points going like that. This is a cubic function. And in cycle 8, I want to say this was, I'm going to, h of x, question mark, which I think is right, but I don't want to guarantee that. Okay, and now let's take a look at our next friend, which is cube root of x. Now, you might be thinking to yourself, well, if we had a squaring something and then square rooting something, if we are cubing something and now we cube root something, we're doing the same type of thing we just did. This is going to end up with points again that we can only choose certain numbers that come out nice. 0, the cube root of 0 is going to be 0. 1 is 1, and negative 1 would be negative 1. But then the next perfect cube that I have is 8, which would give me 2, and then I've got negative 8, which will give me negative 2. And just so that you know, if you're, by the way, this is k of x, if you're using a TI 80-something calculator, it's going to be under the math button, and there's going to be the symbol for cube root that you'll see. If you are using a Casio, so this is TI, Casio, you may have to type in the number 3 and use the X root button and then type in whatever you want. And if you do that like this, it should give you 2 as an output. Okay, but graphing these points, so we got 8, 2. We got 1, 1, 0, negative 1, negative 1, and then we've got negative 8, negative 2. And I'd like you to notice that compared to the table for x cubed, which was negative 2, negative 8, negative 1, negative 1, my x and y are swapped. These are inverses also. So the cube root and x cubed are inverses. Okay, now we get into the fun stuff. So we've got to do a couple of different things here. The first we're asked to do is to sketch a graph of the mother function that we're dealing with. So we've got to figure out what the mother function for 2 square root of x plus 1 is. And the mother function of this is going to be the square root of x. I know this because I can see that that is a square root function. So just to steal the points we had on the other one, that was 0, 0, 1, 1, 4, 2, and 9, 3. And let's plot those points. 0, 0, 1, 1, 4, 2. We got 9, 3. And that's going to keep going after that. And then we got to find 2 times the square root of x plus 1. What I'd like you to notice is that we have something that's kind of interesting here. We have a function notation that looks a little bit different than what we were doing last week. What we were doing last week, this would have been written as 2, and square roots, I think, were g of x plus 1. What we've done is replaced the g with this square root notation. Otherwise, everything else stays exactly the same and has the same exact meaning. So we know that on the inside, x plus 1 means that we're going left 1. So my x values, 0 would become negative 1. 1 would become 0, 4 would become 3, and 9 would become 8. And the number out front, which we used to call the amplitude in trig, is going to be a vertical stretch, and that's going to be multiplied by a factor of 2. So all of our y values are going to be multiplied by 2. 2 times 0 is going to be 0. 2 times 1 is 2. 2 times 2 is 4, and 2 times 3 is 6. This is the same exact thing we were doing in the last cycle, but now we're adding a new way to notate this, using a square root instead of just the letter g of x. So my new points are going to be negative 1, 0. That's here. 0, 2. 3, 4. And 8, 6. Nice smooth curve through there. And what's going on here is that we have a graph that has been moved to the left and stretched vertically. Let's revisit domain and range. I'm going to do these for the blue graph, not for the red graph. So the domain, my blue graph starts at -1, and it keeps going off my paper, so I'm going to call that infinity. For the range, I start at a height of 0, and it keeps going up off the paper, so that's going to be infinity as well. X-intercept, I hit at the point -1, 0. The y-intercept, I hit at the point 0, 2. It is increasing for its entire domain, so it's going up and to the right the entire time. That's -1 to infinity. It's never decreasing. Its minimum is at -1, 0. And it doesn't have a maximum because it keeps going up forever. It's never negative because it's never below the x-axis, and it's positive the whole time, so -1 to infinity. Okay, next up we've got the quantity x plus 2 squared, and what I notice here is the squared piece, and I've got stuff on the inside, so this mother function is going to be x squared. What we're trying to do is see that we have this stuff squared, and that stuff happens to be x plus 2. This would be the same thing as in the last cycle if we wrote f of x plus 2. So we know a couple things. We know what transformation this is. This means left 2. It also lets us build some tables. Okay, I'm going to start with the same table we had for our mother function. We went -2, 4, -1, 1. I'm going to skip 0 just so I can get 1, 1, and 2, 4 in. But we got our lovely graph looking something a bit like this. So then if we talk about, this means left 2, that -4 would become, -2 would become -4. -1 becomes -3, 1 would become -1, and 2 would become 0. But we're not doing anything to our y value, so those stay the same, 4, 1, 1, and 4. So literally what we're doing is we're taking each point of our graph and shifting it 2 units to the left. And I am misreading my graph. So that one's I'm going to erase that with my eraser because I can. That one's going to go there. This one is going to go there. That's going to go there, and that's going to go. Oh boy, that's fun. Undo that. There we go. Oh, sorry, there's a toolbar in my way, making that hard to see. And we're good. Okay, I'm going to draw arrows at the end of this, showing this is going up and to the left and up and to the right forever. Domain, since I'm going off my graph in both directions and keep going, we say the domain for this is -infinity to infinity. For the range, I don't go any lower than 0. That's my lowest y value, but I go up forever. X-intercepts, I've got -2, 0. And a y-intercept, we've got 0, 4. It is increasing. We're starting to increase at -2 and going on forever. So that's this part of the graph here. And then decreasing, that starts at -infinity, so all the way to the left side, and stops at -2. It's got a minimum at -2, 0. It's never got a maximum because we go off into infinity. It's never negative because we're above the x-axis the whole time, and it's always positive, and the whole domain is -infinity to infinity. Here we've got the function, -2 times the cube root of x minus 3. I'd like us to identify the mother function is the cube root of x, and just to remind ourselves, those were points like -1, 0, 0, all the nice cube numbers. 1, 1, and positive 8 and 2. And just as a reminder that what we have now is 2 times the cube root of x minus 3 is equivalent to saying, based on our notation from last week, and I think we called this k of x minus 3. So in looking at this graph, we end up having two transformations happening. It's going to go right 3, and, ooh, this is going to be interesting. We've got a vertical stretch. I'm going to call this times -2. What that's really going to end up doing is having a flip as well, so that when we go 3 to the right, we end up at, okay, that's 2, 3, 4, and 11. I like that I wrote that in the x column. Oh, well. And then the new y values to match that are going to end up being this times -2. So positive 2, 0, -2, and -4. Okay, let's plot those points. I'm going to plot my original graph first. So there's my 0, 0, 1, 1, -1, -1. I could have also had -8, comma -2, 5, 6, 7, 8, and 5, 6, 7, 8. All right, and do my other graph in green. We're going to have 2, 2, which is here. We're going to have 3, 0. We're going to have 4, -2, and 11, -4. It should be down there. I'm going to erase that one as well. I always forget I have an eraser on this. And when I do that graph up, we end up with something that looks like this. So you end up with a vertical flip as well as a stretch because of that negative. In looking at some of these things, some of these are easier than others. The x-intercept, I see at 3, 0. The domain and range, I'm going up and down. I'm going left and right. In both of those cases, we're going from -infinity to infinity. This one does have positive and negative places. It's positive everywhere from -infinity all the way up until 3. And it's negative from 3 all the way up into infinity. We always use our x values for this. We don't have a max because we are increasing forever going to the left. That's poor wording of my choice. We don't have a min because we are going to infinity in both directions. And as far as a y-intercept, it's not actually going to be at 4. So it's what would happen if I plugged in 0. And that would end up being -2 times the cube root. 0 minus 3 is -3, which does not come out as a nice number. So I'm just going to leave it like that. My graph, the green one, is increasing never. And it is decreasing the entire time, so from -infinity to positive infinity. And the last of these, we have x plus 1 cubed minus 2. And I'm going to identify the mother function as x cubed, because that's going to be like this stuff cubed. In this case, that stuff is x plus 1. And then afterwards, we're minusing 2. In the parlance of last week, this would have been identified as h of x plus 1. That's the x cubed part. And then minus 2, which gives us two different transformations. We are going left 1 and down 2. Okay, so if we build the mother function table, we're going to use the same one we did before. So we got -2 and -8. -1, -1, 0, 0, 1, 1, and I'll add an extra row for bonus of 2 and 8. Might as well graph that as well. So we've got 0, there's my 1, 2, 8. It's my -1 and -2, -8. That nice smooth curve. And now let's build our transform table. So based on this, we've got left 1 and down 2. Left 1 means that we're going to be at -3, -2, -1, 0, and 1. And then down 2, each of those would be at -10, -3, -2, -1, and 6 respectively. So if I plot those points, we got 1, 6. We got 0, -1, -1, -2, -2, -3, and -3, -10, giving me a graph that looks like this, which looks like it's left and down of where it used to be. Because we're going off the map on both sides of this, both positive in the y and x direction, negative in the y and x direction, the domain would be from -infinity to infinity. The range would also be from -infinity to infinity. The new x-intercept is going to be at kind of an unpleasant point for us to find because I can't really see when y equals 0 what that would be. So I'm going to put a squiggle there because we don't have the math yet to really dive into that. The y-intercept is a little bit easier. That one is one of the points we found. That's at 0, -1, increasing the whole time, so we're going to use the x values -infinity to infinity, decreasing never, and just like before, we have no max and no min. I like where they started writing nope with a P. That's helpful. And that's because we are increasing forever. We do have a negative and positive value here. I'm going to call this value A because we have not solved for that. So we are positive at every point after A, and we are negative at every point before A, so -infinity up to A.